All right, so we got in the middle. Well, we did this derivative. Let's make sure that you understand. The method I use, it's handy. We had a fraction. You could have used the quotient rule, but because the numerator was really just a constant or really a coefficient, I took the denominator, which is where the juice was at, and I made it to the -1. Now, if you make it to the -1, then you can do the chain rule. Make sure you get this -1. That came from the derivative of the inside. That's the derivative of the exponent. And then I know the bell rang, but we end up cleaning this up a little bit. Okay, -100 times -1 is 100. This e to the 3 minus t, nothing happened. Exponent became positive. Exponent became positive. Nice little derivative. Okay, now a nice little derivative will give you a nice little slope, which is really what this question is supposed to be. So let me get those questions back up. We're trying to find the rate. And again, we gave a little hint that the rate is who knows what's going to happen here. There's like, the rate is the slope of the tangent. So if I want to know the rate on day 3, what I really want to know is the slope on day 3. And so it's time to plug in 3. We will talk more about this. We will talk more about how rates are slopes, but at least you heard it here kind of for the first time. Listen, this is what we would commonly call a textbook problem. The numbers, it's kind of made to work out nicely. So even if you don't want to type this in your calculator, just look, you get e to the 0. Well, that's 1. So that's 100. And I get another e to the 0. That's 1 plus 1 squared. So I have 1 plus 1 squared. That's the number 4. 100 divided by 4 is 25. Let's talk about that number 25. Some of this I'm just talking about because in a few weeks, more like a few months, but at some time we will be really digging into this. That's a rate. That means that it's per something. It's actually students per day. The reason it's per day is because that's how this equation was measured. Now, what that would mean is that on day 3, it wasn't that there was a total of 25 kids. It was that there was 25 more kids infected. And that would mean on day 2, there were some students that were infected. And on day 1, there were students infected. But now that we get to day 3, there's 25 more. That's what we mean by it being a rate. Which kind of leads us to this last question here. The fastest rate. The fastest rate. I'm going to appeal to a graphing solution here. Now, there's 2 places we can go to see rates. You've actually gone to these places. I had you do it in that investigation a couple weeks ago. One of the places you can go is to the original equation, because the original equation, of course, has slopes. It has slopes denoted by the shape of the graph. Now, I'm carefully typing in the original equation, just double checking here, parentheses. Okay. I'm also going to have to change the window for those that are playing along. You'd have to do this kind of thinking. The x value is days. We don't really have specifically anything up here about days, but I can just tell you that we don't need to go anywhere beyond a month. We don't have to go anywhere beyond 30 days. And the y value is the total number of kids. We don't really know what that is, but I can see that on day 3, I was already up to 25 kids. I'm going to I'm going to go 0 to 200 here just to make sure that I have enough. Now, the graph I'm going to show you, even if you're just watching, the graph I'm showing you is the graph of the total number of students infected. Okay, and as you can see, there's some significant change in the beginning. We also seem to have a lot of wasted space here. You know what? I must have used a little too much X, so I'm gonna fix that. I'm only gonna go 15 days. I thought maybe we needed a month, but I'm gonna go 15 days, a half a month. It just spreads it out a little more. Now you can see here that in the first about 10 days, there's lots of change. But what I really want you to see is right here in the middle, we would argue that the graph would be the steepest. The graph would be the steepest because it's kind of climbing up to that spot. Okay. In other words, it's kind of curving up. In a few weeks, we'll call that concavity. And then it starts to curve down. So at this spot right in the middle, we would say that we have the fastest rate because of like the curve of the graph. Okay, now it just so happens that that spot in the middle was the number 3 that we found through some of that work. Now, are you still with me here? If you're with me, you might be like, wait a minute, whoa, that says 350. That says 3,50. Nothing's wrong. That's because that graph is showing you the total number of kids. That means on day 3, I have 50 kids infected. Remember, this was the rate. That meant on day 3 that I added 25 kids. Okay, but because of the shape of the graph, I would say that I have the fastest rate at day 3. Wouldn't hurt to probably draw the graph. But again, we have day 3 here. Now, there's one more place you can go to see rates. This is kind of heavy stuff, okay? And maybe if you're totally honest, you might be like, yeah, I don't know if I quite get all that. I'm just trying to preview it because we're going to come back to this in the next chapter. But the other place that we can go to see a rate is literally to the graph of the derivative. The graph of the derivative. Okay? It's a little bit more to type in, but even if you're not typing in, try to understand what I'm doing here. I am graphing the derivative. What happens when you graph the derivative? Well, you see the slopes just in a little different way. You see the slopes in a little different way. I'm going to sort of see what happens with my window because sometimes you have to do the same thing. So I left my window the same and I see that there's a lot of wasted space. So I can kind of go back. I can change my window, particularly the Y value, because I got all that wasted space up there. I'm going to back that all the way back down to 50. It's not the same graph, okay? Obviously, if you look at the equations, they are 2 different equations, but it's not the same graph because it's saying something different. What's it saying? Speak to me, graph. It's saying that as you move along here to different X values, you would get different slope values. And I'm trying to go to a special spot here. I'm trying to go to 3 because I want to show you that up there at X equals 3, I have the biggest Y value, of 25. What is 25? It's the slope right there. Okay, it's the slope right there. So I can look at that graph and I can kind of look for the biggest Y value, and that biggest Y value would be my biggest slope, which matches with the other graph. This is quite an advanced look at a position graph from your physics class and then your velocity graph. Okay, because honestly, this second graph right here is like a velocity graph. It's like the rate. But as I'm being honest, it's an advanced look at this. If you took physics last year and you tried to draw, those different graphs, I don't know if you would have drawn one of this kind of shape, but they are saying the same thing. They're saying that the fastest rate happens at day 3. This is the way a virus usually spreads. Again, I'm not like a medical professional, but it typically has a fastest day. That would be a good day to not be here. If you somehow knew, that would be a day not to show up, because that's when the most spread's going to occur. And then eventually it stops spreading. I mean, you guys saw how this graph got flat. The reason it got flat is because there's no more spread. Okay, and then eventually you just cut it off, because that means the virus is over. Same thing here. Okay, eventually it starts to approach 0. I'm talking about the rate approaches 0. Okay, and when the rate approaches 0, that means no more new infections. And that's, of course, good news. I guess we'll see, again, with this coronavirus, it's just a whole different thing. Ready to do another derivative? Okay, we have the derivative of e to the x. And the derivative of e to the x is e to the x. But what about the derivative of, let me make sure I show this right. What about the derivative of something else to the x? You say, what do you mean something else to the x? Well, you've seen math equations enough. You know that e to the x is not the only exponential. What about 2 to the x? What about 2 to the x? Now, you don't really know what it is, but you're a smart group. You know that it's of the same family, and so I can kind of crank this out quickly for you, because we can do this little graphing trick. We can do the derivative of 2 to the x. Okay, so I'm doing the derivative of 2 to the x. Now I'm doing it graphically. Let me just make sure the window is going to help us. Now here comes the derivative of 2 to the x. I could make that window work a little bit better so we get the full effect here. Here comes the derivative one more time. I know you're not into memorizing graphs, but again, you're sitting in a math class. You have to look at that graph and say, okay, that's exponential. Oh, wait a minute. The derivative is exponential. Does that mean that the actual answer is, once again, 2 to the x? Now watch, I'm going to graph 2 to the x, which is kind of like our supposed prediction. I want you to look at that and say, close. In other words, the derivative seems like it would have to have in its essence the same thing. But we can't stop at that. We can't say that that's true, not without a little bit of a adjustment, a little bit of a fix. Now, I'll give you a hint if you want to play along a little bit here. You have to multiply it by something. Any guesses? How can you fix the bold line? How can you fix the bold line so that it can kind of move over where the derivative is? I have to multiply it by something. Sometimes somebody will say multiply it by 2. I don't know if those somebodies just aren't here, or but look what happens when you multiply it by 2. You're right. It's not going to make sense. Look what's going to happen here. Here's the derivative. Takes a little while because it's cranking out the answers. There's the derivative. This is what happens when you multiply it by 2. You actually exacerbated the problem. You made it get further away. You made it get further away.
What about multiplying it by negative?
We have to watch this thing again. Here comes the derivative, slow and steady. Here comes negative 2. Oh, Well, the reason you're not seeing is because it reflected, right? It's down there. I'm not going to redraw it, but it's down. But you're thinking, I like it. 3. Let's show it. Remember, when you multiply a graph by a number, you're just making it increase more quickly. But that's if you multiply it by a number greater than 1. So I like that you said that, because now we can see that it's like further away. That's because it's increasing too quickly. That's because you multiply by a number greater than 1. It has to be a number less than 1. That'll sort of push it back down. Well, like I said, there's no reason you would know this. So I'm just going to show you. It was close to the number 2. It's actually the ln of 2. Now the ln of 2 would actually be like the exponent that would go on the letter E to get 2. That's theory, but it's a special number. And what you're going to see here is that it makes it match. It makes it match. Here comes the ln of, or 2 to the x, the ln of 2. They're exactly the same. Make sure you write it correctly in your notes. It's 2 to the x times the ln of 2. It's like a little adjustment. It's a little adjustment. If you have a to the u, if you have a to the u, in other words, any base, the derivative of a to the u is still a to the u. That's the whole cool thing here. It's still a to the u. But then you have to adjust it. It's the ln of a. It's like a little adjustment. It's the ln of a. And then there's always a du dx. Du dx just stands for the derivative of the inside, the derivative of the exponent. Let's do a couple more derivatives. Hopefully show you that this is a pretty easy rule. It is a rule though, okay? It's a rule, so you have to follow it. Now, it's usually pretty easy for kids to say, okay, yeah, 16 to the x squared, I'm going to use this rule. It's pretty easy to say that because that's what we just talked about. When you see this problem mixed in with other problems, which is coming on a test, the test is not before break. We would have needed maybe like 1 or 2 more days. So eventually the test is after break. Don't worry about it all break, but it is something you want to be starting to think about. When you see this question mixed in with other questions, the first thing you should say is that it's of the family a to the x, because basically x is in the exponent. And folks, when you're in that family, it's a fun family because the derivatives are the same. Okay, at least in their essence, they're the same. So when you're in that family, the derivatives are the same. Now it's time to fix it. You fix it by multiplying by the ln of 16. That's kind of your adjustment. And it's also necessary that you finish it. And I have to confess, I kind of did this backwards. So my bad. It's the first problem we're doing, and I sort of did it backwards. I should have multiplied by, well, you know what? I didn't really do it backwards. You just need to make sure that you do these 2 adjustments, the ln of 16, and then, of course, you always do the derivative of u, the derivative of the exponent, and that's the chain rule. So, yeah, we can put it in that order. That's the way I wrote it up here. Listen, don't be silly and tell me that this simplifies somehow to be 32. In fact, there's no 32 anywhere. Don't take this 2 times this 16 or times this 16. Again, you don't get a 32 anywhere. You really just get what you have. In fact, most of the time we just leave it like that. As long as you don't change anything to 32, you'll be fine. Here, let's try another one. There's a party. It's the exponential party. So at the door right now is 3 to the tangent of x. So it's allowed to enter the party because the derivative of 3 to the tangent of x is the same thing. Are you writing down the same thing? You're getting it right. The reason I'm trying to share it like that is because I hope you remember when you're taking a test and you're like, oh, shoot, what's the rule? It's the same thing. Write it down, but then fix it. Fix it. Do the ln of the base. Do the ln of 3. Finish it. Do the derivative of the exponent. Now, the derivative of tangent is secant squared. And yeah, like that's fine. The way we're writing that answer is fine. I know sometimes we switch things. Nothing really needs switched. Okay, you're just kind of following the rule. Last one. How about y equals x to the root 3? Y equals x to the root 3. Hello? Can I come into the party? I can't. And the door slams on x to the root 3. It's not allowed into the exponential party. Why not? Is the derivative of x to the 1/3 the same thing? Okay, it's not the same thing because x is not in the exponent. X is in the exponent. You're in the party. X is in the exponent. You're in the party. X is in the base. Oh, what party? That's the one next door. That's the one next door. How do you do a derivative when x is in the base? Well, this is the party that's been going on since like the first day of this chapter. Remember? I hope it's not like boring to you now. But, and by the way, if you didn't see this, sort of join the club. That's why I put it up here. But this is just a power function. Power function. Power rule. Now, if you're wondering how to subtract 1, you literally can just subtract 1. You can show it. Okay, but we did all this fun stuff today, but it only fits if it's exponential. It only fits if it's exponential. Okay, so it depends on where x is located. Here, x is in the base. We have to go back to that party.